Welcome to class number 3, session number 3. This session will focus on the different parameters that characterize a sensor. Validation of sensing results is fulfilled by characterizing one or combination of the following parameters. The first parameter is the accuracy. Accuracy is how close a measured value is to the actual or true value. In the analog of an arrow that is shot towards a target, accuracy means how close the arrow is to the target's center. The second parameter that is important for the validation of the sensing is the precision. Precision means how scattered are the results around an average value. As seen in the analog of an arrow that is shot towards a target, the results cannot be accurate. In this case, it is acceptable to take the average deviation of the arrow's location on the target relative to the center of the target. For sensors to be accurate and precise, the measurements result should be close to the real value and also collected together as seen and demonstrated in the right image on the screen. The sensor sensitivity indicates how much the sensor's output changes when the measured quantity changes. Sensors that measure a very small changes must have very high sensitivity. The sensitivity of the sensor is so far defined as the slope of the output characteristic curve as demonstrated in the plot on the screen. Every device has some amount of noise at its output. The question is, how much is too much? If the signal level is very small, even a very low noise level can have an adverse effect. Therefore, signal-to-noise ratio is a way to appreciate if the signal is high enough in comparison to the noise. This requires actually two-level measurements, followed by a simple calculation. The first step is measuring the output level of the device under test with no input signal. On the other hand, the second step is to apply a signal to the device and to take another level of measurements. The deviation of the two results will output the signal-to-noise ratio. The lowest concentration value that can be detected by the sensor is defined the signal-to-noise ratio, and it's usually equal to the number 3. This concentration will be the so-called detection limit. In this context, I would like to clarify and to warn to make a clear differentiation between the detection limit and sensitivities, as many mistakes has been done in this endeavor so far. The dynamic range of the sensor is the maximum and minimum values of applied parameter that can be measured. Every sensor is designed to work over a specified range. The design ranges are usually fixed, and if exceeded, result in permanent damage or to destruction of the sensor. It is customary to use transducing elements over only the part of their range where they provide predictable performance and often enhance linearity. We will move now to the definition of selectivity. Selectivity refers to characteristics that determine whether a sensor can respond selectively to a group of analytes or even specifically to a single analyte. For example, when an ideal selective sensor is exposed to a mixture of molecules, it interacts with those for which the sensor is selective and rejects the other intervening molecules. The other feature which we will define right now is the so-called linearity. Linearity is the relative deviation of sensing behavior from ideal straight line. Ideal sensors are designed to be linear or linear to some simple mathematical function of the measurement, typically logarithmic. In practice, the relationship between the measured and the output of most transducers is not perfectly linear, and it is therefore necessary to find a way of using these devices to achieve the most accurate overall results. This can be achieved by constructing what is known as the best fit straight line. Other features of the sensors is called resolution. This specification is the smallest detectable incremental change of input parameter that can be detected in the output signal. Often in a digital display, the least significant digit will fluctuate, indicating that changes of that magnitude are only just resolved. Response time. The response time is the time taken by a sensor to approach its true output when subjected to a step input, and this is again is called as response time. Usually, response time is specified as time to raise to 90% of the final value measured from the onset of step input change in measured variable. Hysteresis. Hysteresis refers to the characteristic that a transducer has in being unable to repeat faithfully in the opposite direction of operation, and in this case, the data that have been recording in one direction is different than that has been recorded in the other direction. Hysteresis is a major problem for sensing application, as two signals might be obtained for the same concentration, for example, depending on the directionality of the concentration. Life cycle. Life cycle is the period of time over which the sensor will continuously operate. With this feature, we come now to the conclusions. For conclusion, we got to know some sensor characteristics that have to be taken into account when planning our sensors. With this, we come now to the end of class number 3, session number 3. Thank you.